Hello. In this video, we will be looking at how the NES draws objects, also known as sprites, on the screen. This video is part of a series where I build an NES emulator in order to understand how the system works. In case you're new here, I'll leave a link to the first video in this series. When the NES draws the screen, it is essentially made up of two parts. First is the background, and then is the sprites. Backgrounds are typically used for level data, and sprites are used for more dynamic things that move around. Here we can see a full frame of NES graphics. Here is the background layer, and here is the sprite layer. Combining these gives us the full frame. And before we dive in, a quick disclaimer. The graphics chip, or PPU, used in the NES is very complex. Rather than immediately cover how the chip works internally, we'll look at it from a more abstract perspective. We'll see how software on the NES draws sprites, and we'll look at a simple model for how the graphics chip could be drawing these sprites. This way of understanding graphics is sufficient for most homebrew development, and also covers how most games interact with the graphics chip. But there are some special effects that rely on subtle internal details of the PPU. These will be covered in a future video. And with that out of the way, let's take a look at the sprite features of the NES. Sprites are individual tiles that can be positioned anywhere on the screen. The NES can store information about 64 sprites to draw at once. Due to some particulars of the internal implementation, only 8 sprites can actually be drawn on any horizontal line. If more than 8 sprites are specified, only the leftmost 8 will actually be drawn. Sprites can be drawn with various attributes, including which tile image was selected, the position, the selected palette, flipping information, such as flipping horizontally or vertically, and whether or not the sprite is 8 or 16 pixels tall. We'll start by understanding sprite rendering by looking at the simplest case first. Sprite drawing is handled by the PPU chip. In order for the PPU to know what sprite to draw, the CPU needs to send the appropriate commands to the PPU. Just as with the palette information that we saw for color, this is accomplished via MMIO, or memory mapped I/O. Sprite information is stored in a special memory region within the PPU chip called Object Attribute Memory, or OAM. This stores information for the 64 sprites and uses 4 bytes for each sprite. Since all of this information is inside the PPU, rather than residing in VRAM, as was the case for the palette and character data, new MMIO addresses are used to control this data. Let's take a look at these. First, at hex 2003 is what is known as OAM address. This is write-only. This specifies which byte within OAM will be updated. This starts counting at 0. Then we have hex 2004, which is OAMData. This can be read and written to. Writing to this address will update OAM at the address previously specified by writing to OAM address. Writing here also increments the internal OAM address. Finally, hex 4014 is OAMDMA. Writing a single byte here is a way of telling the PPU to copy an entire page. This is much faster than many writes to OAM data. We'll come back to this in a little bit. You may have noticed that the OAM address and OAMData MMIO addresses behave very much like the PPU address and PPU data registers that we saw when we were updating the palette data. Since the OAM is actually inside the PPU chip rather than in external memory, we can't just reuse the PPU address and PPU data registers. Otherwise, the interface is very similar. Let's take a look at what sort of data the OAM actually holds so we can understand what we want to write. That brings us to the layout of the OAM. For each sprite in OAM, the NES stores 4 bytes with various metadata. The first byte is the Y position of the top of the sprite. The second byte is the tile number if drawing a standard 8x8 sprite. Tall sprites, which are 8x16, essentially involve combining 2 8x8 sprites. The logic here is a little trickier, so we'll leave it for another video. Byte 2 is attributes. Each bit within this byte has a different significance. Here we have all the bits numbered. We see that of these bits, some of them control whether or not the sprite is flipped vertically, whether or not it is flipped horizontally. There is a background bit, also known as priority, which controls whether or not this sprite is drawn above or behind the background. Some of the bits in the middle are actually unused. And finally, the least significant 2 bits are used to select the palette that will be used when drawing the sprite. And finally, we have byte 3, which holds the X position of the left of the sprite. Now that we know what goes where in OAM, let's write a simple program to just draw a sprite in the very middle of the screen. To center the sprite, we have to calculate the X and Y coordinates of the upper left-hand corner of the sprite. Let's do the Y coordinate first. Essentially, we take the height of the screen, subtract the height used for the sprite, and just divide that by 2. The NES display is 256 pixels wide and 240 pixels tall. So 240 minus 8 over 2 is 116. And in hex, this is 0x74. Doing the same thing for the x-coordinate. This time we have 256 for the width of the screen, 8 pixels for the width of the sprite again, divided by 2, gives us 124, or hex 7c. So now we know that byte 0 should be hex 74, and byte 3 should be hex 7c. Byte 1 is very simple and just selects a sprite number. For demonstration purposes, I've created a simple character ROM that contains only a single image in tile 1. The sprite is a non-symmetric arrow to make it easy to experiment with the flipping attributes. The nice thing about using tile 1 is that after initializing the OAMData, all these sprites will be using tile 0 by default. So by leaving tile 0 empty, we don't have to worry about unspecified sprites showing up on the screen. And initially, we can just use 0 for all the attributes. After having something basic on the screen, you can go ahead and try changing to experiment with these other features. So finally, the 4 bytes that we need to write into OAM for this centered sprite, 74, 01, 00, 7c. Now let's go ahead and write a little program to copy this information into the OAM region of the PPU. If you watched the palette video, this will look very similar. Essentially, we initialize OAM address, loading it into the accumulator, and then storing the accumulator to the MMIO address we saw earlier. Then we perform a series of writes by first copying the value that we want into the accumulator, and then storing the accumulator into the appropriate address. Since OAM address increments automatically, we can just go ahead and essentially write to the OAMData address for each of these values. And once we have the OAMData set up, we also want to configure the palette so that the sprite actually shows up rather than using the same colors as is used for the background. We will want to update the palette at position 4, which happens to be the first foreground palette. Once we have that all written, here is what the little test ROM should look like when you run it. I'll include the full source code for this demo, as well as the assembled .nes file. Alright, now that we have the simple form of sprite graphics working, let's go ahead and take a look in more detail at the OAMDMA. We saw that even using a single sprite, using OAM address and OAMData was pretty tedious. And one detail that we haven't discussed too much yet is that OAMData has similar sort of timing restrictions as we saw for the palette data. If the OAM information is updated while the PPU is actively drawing the screen, it can lead to graphical corruption. So in practice, there is a very narrow window of time during which the CPU can safely write to OAM data. Writing into OAM through OAM address and OAM data is quite slow, and needing to do this for 64 sprites can easily spill over the time allocated for updating this information. Fortunately, the NES has a faster and more convenient way to write the entire OAM data. This is the OAMDMA that we saw earlier. Writing a byte, for example ZZ, to OAMDMA results in a full page starting from the address ZZ00 and ending with ZZFF, getting copied from standard CPU memory into the OAM. You may have actually heard of DMA before, and this is a pretty common technique in hardware design. DMA stands for Direct Memory Access, and refers to the fact that this copy is performed without the CPU. Once the CPU starts the transfer, the CPU is paused, and the PPU reads from memory directly. Using OAMDMA is functionally equivalent, though much faster, than repeatedly writing into OAM data. The 64 sprites times 4 bytes per sprite is 256 bytes, perfectly matching the one page that gets copied by OAMDMA. In practice, most software for the NES uses this technique. Software keeps a copy of the desired OAM in main CPU memory, and then uses OAMDMA to copy everything at once to the PPU. If we update our earlier program to instead use OAMDMA, here is what the relevant pieces look like. For this program, we will be using the page starting at hex 0200 for OAM data. In order to write to these higher memory addresses, we essentially need to store a pointer somewhere in the 0 page and use that for these higher writes. We'll do that here. And in order to make sure that we are not copying any sort of uninitialized or garbage information into the PPU, we want to 0 all the bytes within this page. Finally, once the rest of our OAM copy is initialized, we can set up the first position, sprite 0, with the information for the sprite that we actually want to draw. The values that we're writing are exactly the same as before. Here's what it looks like to write these into our copy, and finally, to write the entire OAM copy into PPU OAM memory, we just write the value 2 into this special DMA address. And if you run it, you get exactly the same result that we saw earlier. The benefit to this technique, as mentioned earlier, is that it's much faster. So if you wanted to draw multiple sprites, this is how you would want to do it. And at this point, if you want to experiment with some of the other attributes we saw, like vertical or horizontal flipping, you can go ahead and copy the code that I've provided and update the attribute byte. And that's essentially it for drawing sprites. Next time we'll look at how the background images are drawn. Backgrounds in practice make up most of the information that you see on the screen on the NES. Hope you enjoyed the video. If you did, please consider liking and subscribing. And even better than that, if you know someone else who might like the video, sharing is even more helpful than subscribing and liking. Thanks, hope to see you on the next video.